Step number 2, you have two block system. Block A, mass A, on top block B, mass B on the right side, and the pulley has negligible mass and negligible friction, and the block released from the rest. So it looks like it's a simple system. And if you look at, suppose block A is much greater than B, what is the magnitude of acceleration after release? So if block A is massive, block B is small, yes, acceleration will be smaller, right? So acceleration will be close to 0, I guess. What's the reasoning? Because the whole system moves because of this small mg, and this small mg will feed the acceleration of the system. So the only force will be small mbg. Only force pulling will be small mbg, and that will make m plus m to accelerate. And since force equals ma, the total mass is large, so acceleration will be small. Or actually you can check the systems of equation. So you have ma pulling tension, I'll ignore y directional force, and mass b, there's tension, and there is mbg. So F net for A, the only force is tension, equals mass A times acceleration, and F net B will be mbg, that's the gravity, minus tension. Here always, I know the system goes this way, so you choose winning side as positive, okay? That's why I chose this direction positive and upward direction negative, which is mass BA. If you add them, this tension will cancel out. That means this is internal force. If you look at two block as a system, then you have mass BG on the left equals, if you add these two, you can factor A out. Then you can write MA plus MB. So acceleration will be mbg over ma plus mb. Now, first case, A is much greater, so this guy is very large. Then acceleration will be, basically this is pretty small. So you have large denominator, so acceleration will be close to 0. Okay? It's like infinite here and something small g, small number there. So if this gets large and large and large because of this mass of A, which is on top of the table, this acceleration will be smaller. So one way to say is, since the only force pulling the system is mbg, which is small compared to mass A. F equals ma, F is small, mass is large, so acceleration will be close to 0. Now suppose block A is much less than block B as the magnitude of acceleration. So if block A is small, if this is small and this gets large, So this is not going to feel much of the pull here. So it'll fall as if there's nothing there. So that will be close to G. So oscillation will be close to G or less than G. But since there's certain mass, even if it's small, it's still there. So it's close to G, but it will be slightly less than G, I guess. Explain Bernoulli reasoning that the driving equation. So in this case, the force pulling of the large mass MB is small. So MB will fall as if it is free fall. So I guess that's how you explain. Now suppose neither block's mass is much greater than the other. Okay, so they are like relative size, but they are not necessarily equal. The dots below represent block A and B, indicate the label. The forces represent. So basically, this is what we did up here, but this time you have to include gravity. So block A was here. That's B. So block A, you have tension. I want to make this arrow same size as the tension pulling also. Make this same size. And because even if B is very small mass, this will still slide down because there's no friction pulling back. So I'll guess this is bigger. This arrow has to be longer than this. So you can say FG mass BG. Then you have MAG, which is the gravity. Then you have normal force, which is same size as this. Then drive equation for solution to the block after release. I think that's what we did. So acceleration eventually became MBG over MA plus MB, right? And the derivation was here. All right. If you need, what is it? If you need to draw anything other than what you have shown in part P, assist in your solution. So I guess we did everything. This is scenario part A2 where mass A is much less than mass B. Then A is small. Then if this is close to 0, then the acceleration, it will be MBG over something close to 0 plus MBG. So it's not going to contribute, this value is not going to contribute much on the denominator. So acceleration will be, actually you don't have the gravity here, you don't have the G here, right? So the acceleration will be G, right? So yes, to return the reasoning by addressing y, since the acceleration becomes certain value when MA is much less than B. So you can just explain this because on the denominator you have mass A and mass B. Mass A is getting close to 0, so basically you'll get MBG over MB, which is the gravitational acceleration. While the blocks are accelerating, the tension in the vertical portion of the string is T1. So I guess they are referring to this one. Next, the pulley is negative mass is second pulley with mass not negligible. So now this has mass of pulley. When the blocks are accelerating in this scenario, tension in the vertical portion of string is T2. So basically, First scenario was when this is massless, so that's T1. And second scenario is when this is not massless, which is, I'll call it massive pulley, and there is B. How does the tension compare to each other? All right, let's think about what happened to mass B. Because now you actually have to use the force of the gravity of B to actually rotate this. And remember, if you want to accelerate downward, you also require alpha for the massive pulley. So because now you have to share the force between pulley, your acceleration will be smaller. But if you think about it, your acceleration is actually sum of the two forces, which is tension and mbg, right? That's the gravity. But I already know acceleration will be smaller. That means tension will increase, right? Because if you think about it, F net will be mbg minus tension equals mba. But I know this guy will be smaller. But this you can't change. That means tension will increase, right? So you get T2 will increase. So I guess that's how you explain for this.